learner will generate a hypothesis. Now, what is hypothesis? Can anybody tell me? What do we discussed this term earlier also. What is hypothesis for us? What is hypothesis for us? Anybody? Students? What is a hypothesis?
It's a kind of an assumption.
It's a kind of assumption, right? It's a kind of thing that we have deduced from the given set of example. Now, this could be right, this could be wrong. We don't know. This is a theory, right? It could be absolutely right or it could be absolutely wrong. We don't know. So the idea is based on these training examples, we generate a hypothesis, and the hypothesis about the hypothesis is that this hypothesis is good enough to learn this concept. So from this 10 example, you've learned this hypothesis. So this hypothesis is good enough to learn that concept, which means other than these 10 examples, if 11th example comes in, your learner will be able to classify. It has learned that concept perfectly. So that is the idea about this hypothesis. Now we'll understand what is hypothesis better when we see an example. So we'll just dive in. So our idea, our intention is to not learn any theory concept behind that. So we'll directly go to one example, right? So let's say I'm going to write this, right? If possible, please take it down, right? So there is a training data set for us, right? So it goes something like this: air temperature, humidity, wind, water, and forecast. Okay, this is forecast. So final, there's one column, this one final column, that is enjoy sport, right? So we have these many columns. This is our training example or the training data set. We are showing only 4 examples here, right? The entries are like this. So we have sunny, sunny, rainy, and sunny over here. And the air temperature options are warm, warm, cool, and warm. Then we have normal, high, high, and high. Wind options are strong, 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 and strong. I'm just scribbling it. Water is warm, 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 and then finally it is cold. The forecast is same, same, change, and change, right? So we have again, I mean, I could not write the the column there. So I'm just writing the 4 rows here. It is yes, yes, no, and no. Now this training data set with these 4 example, our intention is our mission learner, our concept learner should learn a concept, right? That on which day will my friend enjoy a particular sport? On which day, days on which, or okay, on which day will my friend enjoy the sport? Right. So the question is on which day my friend will enjoy the sport. So the days, example days are like this. If the day is sunny, warm, normal, strong, warm, and same, then my friend will definitely enjoy that sport, right? So for a day, I have given these many attributes or features, right? So sky, air temperature, humidity, wind, water, forecast, and enjoy sport. They are all the features or the attributes of our training example, right? So these many features or attributes are there. Among these features, enjoy sport is a special feature. This is the target feature or the target attribute, right? Which will tell us what is that concept on that particular day. So what are the 2 classes here? I told you concept learning is based on classes, and I told you there are 2 classes, or it's a binary class problem. What are the 2 classes that we are seeing here, students, in these examples? What does the target attribute says?
Yes and no.
Yes and no. We only have 2 options, yes and no. On day 1, yes, he liked the sport. On day 2 also, he liked the sport. On day 3, he did not like. On day 4, he liked the sport. Now, our intention of concept learning is to learn a hypothesis based on this given training example. And this hypothesis should be consistent with the training example, right? So the term is consistent. So whatever you generate the hypothesis, it should be true for all these four training example, and it should also work for a new example, new test example that could come in. Right? So that's what we try to do over here. Right? Now, to generate such a hypothesis, so when we say a hypothesis H is consistent with all the training examples, right? So if there are, so I have X as my training examples. So X number of training example, I have X1, X2, X3, and X4, four training example. Every training example has a class. There is a class of X1, there is a class of X2, there is a class of X3, and there is a class of X4. Class of X1 obviously is yes, then class of X2 is yes, and so on and so forth. Right? So the intention is the whatever the hypothesis, whatever the class the hypothesis gives for the training example, it should be consistent with the class of the training example. Right? So if I take hypothesis of x1, so if I say take hypothesis of x1, it should be the same as the class or the concept of x1. So whatever your hypothesis categorizes or classifies x1 as, it should be equal. If hypothesis says it is true, then the concept that is existing in the data set should also be true or yes. Right? So that is what we mean by consistent. So I hope you got the idea of what is consistent. Now there are two ways to learn hypothesis, right? So in this particular chapter, there are two ways for us to generate hypothesis from a given set of training example, right? There are two algorithms. One is called as a finders algorithm, another is called as the candidate elimination algorithm. Right. So in fact, in the old syllabus, finders was also one separate program and candidate elimination was a separate program, but you don't have finders as a program. You only have candidate elimination as a program. Right. So candidate elimination is actually an extension of finders. So we will, go ahead to learn about it. Right. Now, whenever I say, what's this hypothesis all about is, a hypothesis, right? So if I say hypothesis is a H value, it is a set of constraints, right? So it is a set of constraints on these attributes, or whatever are the restrictions or the constraints that we place on these attributes are the hypothesis, right? So that's the hypothesis for us. Okay. So what does this actually mean? What this actually means here is, for sky, what is the restriction I have? What for air temperature, what restriction I have? For humidity, what restriction I have, and so on and so forth. Now, what are the possible values of the sky attribute that we are seeing here? If sky is an attribute, if I'm talking of sky, what are the attributes that I'm seeing here? What are the possible values of sky I'm seeing here, students?
Sunny and rainy, ma'am.
Sunny and rainy, right? So sunny and rainy are the two options. So the constraints that I can pose, the possible constraints that I can pose on the sky attribute are, I can restrict that sky should be sunny, or I can restrict that sky should be rainy, or I can restrict that sky can be anything. Question mark means anything, either sunny or rainy. I don't have a restriction, I'm very flexible. So that is a question mark. Or I can say null. That means I say no value is acceptable for sky. So the four possible options for restricting or posing the constraint for the sky attribute are sunny, rainy, question mark, and null. For similarly, for air temperature, we have warm, cool, question mark, and null. For humidity, we have normal, high, question mark. And so question mark and null are additional. Mean when I say question mark, I am not posing any restriction. I'm not posing any constraint at all. I am very flexible. Any value for the sky is acceptable for it to be a positive training example. See, there are generally two kind of training example. It could be a positive training example or a negative training example. It's a binary case. So obviously we have three positive examples here. 1, 2, and 4 are positive example, whereas third is a negative training example. Right? So I'm telling that if I put a question mark here, that simply is understood as any value for sky is acceptable for a training example to be positive. I repeat, if it's a question mark for an attribute, that means any value is acceptable for this attribute for a training example to be classified as positive. If I'm putting null, then that means I'm telling no value is acceptable for this attribute for a training example to be positive. Is it right for me to tell null? It's actually not. If I say no value, it's not true. If it is sunny, then it is positive. If it is rainy, then sometimes it's not positive. So me telling no value is acceptable for sky is actually not right. But that is also one of the option, right? So like that, we have a possibility to pose a restriction or constraints on all the attributes. We pose constraints on all the attributes except the target attribute. So how many such constraints can we pose in every hypothesis, students? In this training example, if I take a hypothesis, can you tell me how many such restrictions can I have? I told you that restrictions or constraints are posed for all the example, for all the attributes except for the target attribute. So how many such constraints can I have in one hypothesis in this data set? ಎಷ್ಟು attributes ಇದೆಯಪ್ಪ? How many attributes do we have here? Except minus the target attribute. Am I audible? Hello? Yeah. How many attributes are there here?
Third one, we are not supposed to consider cool, ma'am.
6 attributes.
Oh, sorry. Yeah, we're not considering the. Oh my God, what happened to it? It's erased this full completely. Yeah, you're not supposed to consider the training attribute. Sorry, the target attribute. So how many such restriction will we have?
6.
6. Perfect. There'll be 6 such attributes. Okay. Okay, let me see if I can write in this page. That'll be great. Okay. Okay, super. Okay. So we'll see now. So we have, now that we understood what are the possible constraints on every hypothesis, there is something called as most general hypothesis, right? And there is something called as most specific hypothesis, right? Most specific hypothesis. Most general hypothesis means you are very flexible. You say any value is acceptable for sky, any value is acceptable for air temperature, any value is acceptable for humidity, wind, water, and forecast. So you are being very generous, right? So you're telling any value is acceptable. How do we read this? Any value is acceptable for these attributes for a training example to be classified as positive. Right, so that's what we're telling. That's not true. That's actually not true, but that's one kind of possibility. Most specific hypothesis means we are very rigid. We're telling no values acceptable. How many such no values? 6. Why 6? There are 6 attributes, so that's why no values acceptable for sky, air temperature, humidity, wind, water, and forecast for a training example to be classified as positive. This is the most general hypothesis and this is the most specific hypothesis. But our actual hypothesis, which fits or which is inconsistent with these training example, lies somewhere in between your most general and most specific. It's not going to be most general, it's not going to be most specific, but it's going to lie somewhere in between the most general and most specific hypothesis. So if you want to write it, so what do we mean by hypothesis? If somebody asks you what is a hypothesis is simply a set of constraints, right? It's a set of constraints that we pose on the attributes of our example. So it's simply a set of constraints in such a way that your hypothesis isn't consistent with the training example. What do I mean by consistent with the training example? If your hypothesis classifies the fourth training example as true, then the concept of x4 should also be true. If hypothesis classifies x4 as false, then the concept of x4 should also be false. So consistent means if this says true, this is also true. If this says false, this is also false. That's what we mean by being consistent. So any question so far, please ask me, students. Is there any question with respect to most general hypothesis and most specific hypothesis, or what we mean by general hypothesis? hypothesis
Excuse me,
and
ma'am.
specific hypothesis. Yeah, please tell me.
And could you please repeat more specific, ma'am? The second one.
Most specific means we are being so rigid that we're telling no value is acceptable for sky. No values meaning basically it means none of the training examples are positive. Right, so to keep it simple, it simply means none of the training. Why none of the training example? No value is acceptable for sky, no value is acceptable for air temperature, no value. So all it's in your hypothesis here is telling all the training examples should be classified as no. But is it true? Is this more specific hypothesis consistent with this training example? It is not, because your hypothesis is telling no value, irrespective of whatever is the value. No value means whatever value is there for sky, whatever value is there for air temperature, your training example will never be positive. Your training example will never be class 1 or yes, right? So that's not true. So your more specific hypothesis is actually not consistent with your training data set. Right? It simply means that way. So any other
Ma'am,
questions? Yeah, please tell me.
ma'am, you said constraint is are the attributes which generate a positive training example, no, ma'am. For
Constraint is simply constraint means restriction. Constraint is a restriction we are posing on the attribute. Constraint is the restriction that we are posing on the attribute.
okay, ma'am, okay.
Okay. Now let's see. Just a second. Okay, now let's quickly see finders very briefly and then go to candidate elimination. Okay, so what happens if I say finders algorithm? What finders does is we'll give you a set of training example like this, and we will say generate a hypothesis which is consistent with the training example, and finders will find the most maximally specific hypothesis with respect to these training example. I repeat, finders will find a maximally specific hypothesis. What is maximum specific with respect to these training example? It will try to find such a hypothesis, and your hypothesis will definitely be consistent. You should never miss this. If your hypothesis consistent, then only it's valid. Otherwise, it's not valid. So how does this finders actually work is, given this set of training example, it will start with the first hypothesis, say H naught, right? And it'll begin with the most specific hypothesis. It will start, step number 1 is initialize H naught to the most specific hypothesis possible. What is the most specific hypothesis possible that we just saw, that we just learned? What is the most specific hypothesis that is possible?
A null.
Value for all the attributes.
All null. How many such nulls? How many such nulls?
6.
6. Why 6? Because there are 6 features or 6 attributes. We don't consider the target attribute. So minus this target attribute, we have 6 attributes, that's why 6 nulls. So initially we are telling, this simply means, initially we are telling that whatever value is there in these 6 attributes, none of the training example will be positive. Right? So we start with this step. This is not actually true. This is not actually correct. Right? So we initially told this. From now on, we'll start going to one training example after the other. So what the learner does, it observes the first training example. When it observes the first training example, it will check its class or its target. Is the first training example a positive training example or a negative training example?
Positive.
It's a positive training example. So what finders does when it encounters a positive training example is, it will simply check the value of the attribute. The attribute is null here and it is sunny over here, right? So we told that nothing is acceptable to be positive, but there are certain values here which are indicating that this training example is positive. So you got to change that completely. So that's why H1 now becomes sunny. Why did I change it to sunny? Because sunny is indicating positive, and air temperature warm is indicating positive, humidity normal is indicating positive, wind strong is indicating positive. I'll continue that here. And water warm is indicating positive, and forecast same is indicating positive. That's why we changed all these null values to these values. Okay, that's your second step. In the third step, what happens? You'll observe, your learner will observe the second training example. When it observes a second training example, even that is a positive training example, right? So it observes, it compares the values. The Sunny here, currently your H1 is telling that for any training example to be classified as positive, these are the restrictions. These are the specific restrictions. We are specific. It should be specifically sunny. This should be specifically warm. This should be specifically normal. This should be specifically strong. This is what your hypothesis is indicating. So is your second training example consistent with the H1? That's what we're trying to see. So is Sunny present here? Yes, Sunny is present here. We told warm should be present for positive. Yes, warm is there. Now your hypothesis is telling there should be not, there should specifically be a normal value for your humidity attribute for a training example to be classified as positive. So can I say H1 is inconsistent with the second training example?
No,
In
ma'am.
this case, I cannot say that because your H1 is telling there should be a specific normal value for humidity, but your training example is indicating that even for high, there is a positive value. That is when we will start generalizing it. So we told sunny, yeah, we are so far correct. We told warm, we are so far correct. But then when we told a restriction normal, that's actually not right. It even in the normal value for humidity, there is a positive example. Even in the high attribute value of humidity, there is a positive example. So which means we simply place a question mark over here. We generalized it. So now we are telling any value. At this point, we are telling any value is acceptable for humidity for it to be classified as positive. So I hope it's clear. If there's any doubt with respect to why I put a question mark, you can ask me. Next, we are telling they should specifically be strong. Yeah, and we are so far right. There is specifically strong. Yeah, not only that, we are specifically saying there should be warm, and we are so far right. And we are specifically saying it should be same, and it is right. So what is your hypothesis 2 indicating now? For any training example to be classified as positive, we expect sky to be sunny, air temperature to be warm, humidity can be anything, wind should be strong, and water should be warm, and forecast should be same. Right? So we're telling we're being, a little flexible here. We're telling any values acceptable for humidity. Now we go ahead, we'll check the second training example, sorry, the third training example. Now, what are we finding about the third training example? Is the third training example a positive or a negative one? Is it a positive training
Negative.
example? It's a negative training example. The thing about find this is it ignores negative, right? So find this completely ignores negative. It does not do anything about negative, right? It simply, does not bother to do anything about the negative training example. Probably why because if I ask you if H2, please, I want some answer for this. I'm going to ask you if H2 is inconsistent with the third training example. Please listen to my question. I'm asking you if H2 is consistent with the third training example. Is it consistent?
It should not be, no, ma'am.
Consistent meaning whatever H2 indicates, X3 or the third training example should also indicate the same. What is H2 indicating for us? H2 is indicating that for any training example, sky should be sunny for it to be positive. What is X2 indicate? X3 indicating for us? Sky is rainy, but it is
Rainy, ma'am.
negative. Sky is rainy, but it is negative. So are we happy? Is H2 consistent with the third training example? Yes or no? Think
No,
carefully
ma'am.
and tell me. Think carefully, think again. I'm just telling H2 is telling that sky should be sunny for positive, air temperature
It is
should be.
consistent.
It is consistent. Why it is consistent? Your
Yeah.
H2 is telling if sky has any other value other than sunny, then it should be negative. If air temperature has any other value other than warm, it should be negative. So that's what it really means. So the very first attribute, your restriction is sky value should be sunny. If it is not sunny, it is negative. Yes, it is not sunny and it is negative. So we are very happy. Right? So that's the analysis
Ma'am,
about it. Yeah.
then most general hypothesis will be consistent with both positive and negative, no, ma'am.
Yeah, that most general means we're telling every training example is positive. Any value is acceptable. But most general is not our answer. That's not our answer. We just want to just start with something that's like our initial point. That's not the answer of our example, or it could be most general in some trainings data set, right? That could be a possibility, but it's not always this answer. Yeah.
Excuse me, ma'am.
Yeah.
H2 states that wind and water should be strong and warm for positive training example.
Hmm.
But then example 3 states that if it's strong and warm, it could be negative training example as well.
Yeah,
So
but
H2 wouldn't be consistent, no, ma'am, if it
no.
is that way.
See what? No. The analysis is simply that whenever we see this hypothesis, we are telling that, see, this hypothesis is not final, right? It's not final, and this is not our final hypothesis generated by finders. We're only considering the training examples so far. From the training examples considered so far, we are clearly telling the first attribute value should be sunny for positive, but we
Yeah.
are finding a mismatch in the very first attribute. Right, so we're finding a mismatch in the very first attribute. And one more thing, yes, whatever point you told Rakshita, that is actually excellent. That okay, probably when we compare the hypothesis with all the attributes of the training example, we got to do something. You got to take some action on that. But the lacuna or the disadvantage of finders is it is not doing anything about negative. Right, we'll start doing something about negative when we go to candidate elimination. But as of now, ideally what the analysis what I just gave you is for our understanding. Finders, what is finders doing? As soon as it is coming to a training example, it's checking its target, and target is negative, so it's happily ignoring it. It's not doing anything about it. Right, so we'll start taking actions on the negative training example in candidate elimination.
Okay,
Right.
ma'am.
Okay. So as of now, I mean, my question of whether H2 is consistent with X3 was only for you, I mean, only to check if you've understood the concept of consistency. Right. Yeah. As of now, it's ignoring the third training example.
Okay.
Yeah.
Excuse me, ma'am.
Yeah.
What if H2 was consistent with the negative example, ma'am?
H2 generally is not consistent with a negative training example, and that does not happen, right? That means, yeah, if that happens, right, that if that situation can happen, that means your training data
Data
set
is
is
wrong.
error prone, right? So your data is error prone. Your data is itself is there's so many noise. That's called as a noisy data, right? So your data is not pure. So that's the say you already excellently told the two disadvantages of finders. So finders is really not going to do anything about the noisy data, and the second thing is finders should have taken some actions about the negative training example. It's ignoring that. These are the lacunas of finders. It's not doing anything about the noisy data. It doesn't know. It's just trusting the examples. Right. Now, okay, so that was about the third training example. So we'll go to the last, your learner will go to the next training example and will start comparing the attribute value. Sunny, so it told that it should be sunny. So it first compare the target attribute. It's a positive training example, so it's very happy about that. So it'll compare the first attribute and whatever your constraint on your hypothesis is. So it's very happy that yeah, I told sunny and it is sunny. So warm, it expected warm and it is warm, so warm is continued. And then it says question mark. Yeah, so question mark, that means any value is acceptable for humidity. So any value is still acceptable. It says there should be strong specifically, and there is strong specifically, right? And it says warm should be there, right? So your your water should be warm for a training example to be positive. But right now, your existing hypothesis is not inconsistent with the four training example, meaning your hypothesis telling water should be warm for it to be positive. But when water is cold, also it is positive. That means we should start generalizing. So I put a question mark there. And we're telling, look, your forecast should be same. Forecast cannot change for it to be positive so far. But now we see that even when the forecast has changed, it's a training positive training example. So that's why we change it to negative. So are there any further things? Not really. So this is the most that's a maximally specific hypothesis, and this is
That is
consistent with
for
the training
H4, no,
exam.
ma'am.
This is yeah, this actually, yeah, is H4. Yeah, it did not do anything about H3. H3 is still the same, right? So H3 no change. H3 was no change. So H3 when the iteration happened for H3 it ignored and H3 was retained as this. So H4 was this and it's consistent. So what do we mean by this hypothesis consistent with the training example? So now can you just compare and tell me this is your final hypothesis. Is your final hypothesis consistent with all x1, x2, x3, x4, all the four examples? Are they consistent? We got to check. So we're telling when sunny, warm, and any value, and any value should be positive. It simply means for any training example to be positive, sky should be sunny. Sky should specifically be sunny. Air temperature should specifically be warm. Humidity can be anything. Wind should be strong. Water can be anything, and forecast can be anything. That's what it really means. So and it is so far, I mean, it is good enough. It is consistent with the training example. Now I need not question you again for what are the lacunas here. The very first lacuna is yeah, it is not bothering to do anything about the negative training example. It did not absolutely take any action about the negative training example. And if your training data is noisy or error prone, it is not going to work properly. These are the two things. And another major lacuna or another major disadvantage over here is this the only possible hypothesis that is consistent with the training example? Now, if I say come up with some other hypothesis other than this, which is consistent with the training example, can you not sit and break your head and come up with another hypothesis? Yes or no? Is this the only possible hypothesis that is consistent with the training example? Is it right for us to say that the hypothesis that we generated with finders is the only possible hypothesis that is consistent with the training data set? Is it right to tell that this is the only possible hypothesis that is consistent with the training data set?
No, ma'am.
This is consistent with the training data set, that is no doubt, but it's not right for us to say this is the only possible hypothesis that is consistent with the training data set. So with that, we start fine tuning finders and we come to candidate elimination. Right? Um, yeah. So what candidate elimination does is it tries to better find us a little bit, right? It just tries to better find us a little bit in a way that one thing about candidate, you can just write it for your reference if you want. Candidate elimination generates a set of hypotheses. How many hypotheses does finders generate that we just saw? How many hypotheses does finders generate, students?
Consistent hypothesis.
One consistent hypothesis. It generates one consistent hypothesis. Now, what your candidate elimination actually does is, so now stepping into candidate elimination, it generates a set of hypotheses, right? Not just one, it generates a set of hypotheses which are consistent with the training examples. That's one thing about it, right? So the second thing about it is it does not ignore the negative training example. It takes action on both positive and negative training example. Right? It takes actions on both positive and negative training examples. So we'll just start seeing how candidate elimination actually works. Now we know two things. We know what is the general boundary, what is the specific boundary, right? So we understand what is the most general boundary, what is the most specific boundary. So the step one of your candidate, see, we are going to do a lot of theory on this. We're going to see the theoretical concepts behind it. We're going to see the algorithm step by step and how you're going to write the algorithm in your exam, right? All that we're going to see. Right now we're doing what is required for us to do the program, and I hope so far there's no confusion. If there is any confusion or if you need any clarification, please stop me. We're going to learn what is hypothesis, what do we mean by consistent hypothesis, what do we mean by a hypothesis satisfying a training example. We're going to see a lot of theorems, we're going to prove those theorems, all that we're going to do. But right now our intention is to only learn this program, so which is why we're just stepping ahead a little fast. Okay, so we know general boundary and we know specific boundary. Your step one of your candidate elimination is it initializes a hypothesis S naught as the most specific hypothesis, and it initializes a hypothesis G naught as the most general hypothesis. So what should be the value of S naught? What should be the value of G naught? Please tell me. This is step 1 of your candidate elimination. It has two boundaries. Your finders has started from only specific boundary, but your candidate elimination is going to start from two boundaries. It's going to start from a general boundary and a specific boundary. And specific is going to move towards general and general is going to move towards specific. So finally somewhere we'll land up and that's going to be our final set of hypothesis. That's what it really means. So tell me what's a more specific hypothesis quickly, students. What's a more specific hypothesis? Yes. What restriction do we have in the case of most specific hypothesis? You're being so rigid. We are basically more specific hypothesis is telling no training example is positive, no value is acceptable, or that's what it means. So what do we place as restriction quickly? Hello?
Null.
Null. Thank you. Yeah, it is null and it's 6 null because there are 6 attributes. And it's 6 question mark here because we are being most general. We're telling any value is acceptable. Right. So now we start with the first training example. Right. So when we start the first training example, right. So we check the class of it. We check the target of it. Is it a positive or a negative one? So we see this target and we know that it is a positive training example. If it's a most positive, so generally the idea is if it's positive, we first check the G boundary. And if it's negative, then we check the S boundary first. There's no restriction, there's no hard and fast rule for that, but we generally follow this norm. Even if you check the GS boundary first and then come back to the G boundary, there's no problem with that. Generally, if it's a positive example, we first go to the G boundary. So is G not consistent with the first training example? So I know probably this is a lengthier class and I don't know how much you're able to get it as well. I would appreciate if I get some response. So that'll help me move ahead faster. So is G naught consistent with X1?
Yes, ma'am.
Thank you. Right? Do you all agree? Is there anybody who doesn't agree that G naught is? So we are telling in G naught, we are telling any value is acceptable to be positive. So yes, there are some values and it's positive. So we're very happy. So G1, when I move to G1 from G naught, I don't have any change. I told you any value is acceptable, and so far any value is acceptable to be positive. It's only so far. We don't know what happens in future, right? Now we'll go to the specific boundary. Now what are we telling? No, see from specific, whenever we start moving from the specific boundary to general boundary, that's exactly the find this algorithm, whatever we did. Now currently we're telling no values acceptable for any of the attribute for a training example to be positive. Are we right? Is S not consistent with the first training example? Can I say that S naught is consistent with the first training example?
No.
It is not consistent. Now, one more question before we proceed. What if your first training example was negative? If your first training example was negative, is S not consistent with X1 in that case? If it was negative. If it was negative, would S not be consistent with the first training example?
Yes, ma'am.
Yes,
But
ma'am.
G not.
Yes, yes, yeah, but G naught would not be consistent. Yeah, that I know. That's right. So when we say if it was a negative training example, your hypothesis is telling, look, no value is acceptable to be positive, and your training example is depicting that. So S naught would be very happy in that case. But currently, it's a positive training example, so S naught is not consistent. So we got to do some changes. So what do we say? We said no value is acceptable. That's not true. Sunny is acceptable. It's exactly find S. Warm is acceptable and normal is acceptable, and similarly strong is acceptable, warm is acceptable, and same is acceptable. I hope no questions so far or no clarifications. If you have, please ask me. We'll check the second training example. When we see the second training example, it's a positive training example. I told you generally we follow this norm that we go to the G boundary first. So is G1 consistent with the second training example? Is G1 consistent with the second training example, students?
Yes, ma'am.
Yes. So G2 also, G1 is also very happy. That means G2 also is going to be the same thing. But when we come to this, when we check with S1 and S2, they're not really consistent because humidity is indicating normal, but humidity high is also positive. So we got to do some changes exactly the way we did in Finders. So it's still sunny and sunny. It's still warm and warm, but it's not normal. We are generalizing it. It's still indicating strong. So strong is acceptable. It's still saying warm and it's still saying same. We'll go to the next training example. The next training example is a negative training example. Finders did not bother to do any action on that. But we now go to the S boundary, right? So generally we start negative, we start with the S boundary. Now the question is, now the question what I asked you. Is the specific boundary hypothesis is inconsistent with this? It is inconsistent. We've agreed that it is inconsistent because your hypothesis is going to classify a training example as positive and all these restrictions are true. But the very first restriction is not true. So definitely any training example which fails for any of these restriction will fail to be positive. And it is true, right? So even though there is strong here, even though there is warm here, even though there is same here, there are certain changes, there are certain mismatches. So X3 isn't consistent with S2. So we will retain S3 to be the same thing. We will retain S3 to be the same thing. But when we come here, when we come to the G boundary, we're telling any value is acceptable for positive. No, that's dangerous because not every value is positive. There are certain values which are indicating negative action, right? So that are indicating negative action. Now, please observe, student. This is a tricky point. This requires your concentration. Now, what we do here is we consider one question mark at a time, or one you know ambiguity that we have here at a time, and we try to take the opposite of it. Here we're telling any value is acceptable, but rainy is actually not acceptable. What's the opposite, or what are the other options other than rainy that we can see for this attribute here? Sunny. So I say sunny. Look, it should be sunny. It cannot be rainy. It should be sunny. And I remain the other question marks as it is. Remaining 5 question marks as it is. Right. Now I take the second question mark. It says cool is not acceptable to be positive. Cool is negative. So I should take the opposites of it. What are the opposite that I can see? What's the opposite that I can see?
Warm.
Warm. So I got to place here warm. Right, so I got to place here warm and the remaining question marks as it is. Similarly, for the third question mark, I see high here. I see high here. I take the opposite of it, right? Yeah, I know you're probably getting a lot of questions at this point, right? So there is high here, so I take normal and I remain the other question marks as it is. Then we check strong. Do I see any opposite or any other possibility other than strong over here? This only strong, right? There's no other option for me. So I don't really bother to do anything for the fourth question mark. When I consider the fifth question mark, there's warm here and I got to take the opposite of it. So that is cold, right? I'm just writing that here. I'm just writing that here. Cold and one question mark. Then finally, I consider the last question mark. There is change here. I got to take the opposite of it. And the opposite of that is same. Right, so that's how I wrote these many hypotheses. So your G3 set has how many? 5 hypotheses. But among these 5 hypotheses, I cannot finalize G3 to be this. I got to check if all these 5 are consistent, right? Consistent with the positive training examples encountered so far. I repeat, when we said that when we change the G boundary, we have to check. If you want, please note it somewhere. It's very, very important. When we set the G boundary, we got to check if the G boundary is inconsistent with the positive training examples encountered so far. So we have encountered only 2 examples which are positive so far. And is sunny with all question mark right? Yeah, they are consistent. So sunny with anything, and you're not worried what is there here. So it is consistent. So sunny with anything is consistent with x1 and x2. And warm with any possibility, that's also consistent. Is normal with any possibility consistent? Is this hypothesis, is this third hypothesis that I'm seeing consistent with x1 and x2? It is not consistent, right? So this is absolutely not consistent, right? And what about the next training example? Is it sorry, that's sorry, this hypothesis. It says cold. So is it consistent? Can I say this warm and warm here and it's indicating cold? So this also not consistent. I'm going to remove that. But same is still holding good. So your G3, though it actually generated 5, it's going to be retained with only 3. Are we happy so far, students? Any questions or any clarifications? Please ask me. Okay, I'll take that you understood. Now the next train, the last
Ma'am,
training yeah, please tell me.
here we have only two sets of attributes, that is sunny and rainy. What
Mm.
if there were three, ma'am?
If there was three, for example, let's say sunny, very sunny and rainy, but rainy is indicating a negative example, means I should have one hypothesis for sunny, next hypothesis for very sunny. Similarly, if it was warm and very warm or for some other value, then I should have warm and one more of that option. I should generate all the opposites. Here there were only one opposite. For any there was only one opposite, so I have only one. If there was one more opposite or even two more opposite, I have to generate hypothesis for all those opposites. Okay, we'll do a lot of example, not today, but when we do a lot of examples, we will take such scenarios where there is not just one opposite. Here we are seeing only one opposite of cool, one opposite of warm, but there will be scenario where there are more than one opposite or more than one possibility for the opposites. Right. Okay, now let's go to the fourth training example. The fourth training example is a positive training example. We generally follow this, that we go to the G boundary first. So we check, the question is everything that's there in the G boundary consistent with this training example? Sunny with everything, yes, it is consistent. So G4 will retain that. So sunny with all the question mark. Warm with all the remaining question mark, it's still consistent, so it's going to retain that as well, right? And then your hypothesis is indicating that forecast should be same for positive. So is this consistent with x4? The third hypothesis in G3, is it consistent with x4, students?
No, ma'am.
No.
It's not. If it's not consistent, what do? We ignore it. We don't consider it in the next case. So G4 only will have two possibilities. Now we go to the specific boundary. So specific is very similar to find this. So what's now? So your S3 was telling there should be sunny. It's still sunny. So we're very happy. It's still warm. It says warm. Anything. It's anything. So no problem. Strong. So it's still strong. And it says warm, but there's cold. So there should be question mark and there is same. Do we have any further training examples? Should your learner learn on any further training examples? Not really. We're done with all the training examples. So our final answer is this. Right? So our final answer is this. Right?
In
Yeah.
S4, in S4, shouldn't it be question mark for same, ma'am? Because it is change.
Oh yeah, sorry. This should be question mark. This should be question mark. Thank you. It should be question mark. So these are the set of hypotheses that are consistent with the training example. Now the idea is finally there should be so many training examples given to our learner in such a way that S4 constantly keeps moving to the G boundary, constantly moves to the G boundary and G constantly moves to the S boundary, and at some point they must converge and finally one hypothesis should come out, right? That's the whole idea. So for that there should be lots and lots of training examples and absolutely noise free data. Even candidate elimination really fails if there is a noisy data meaning if your data itself is error prone, if your data itself is wrong, then your concept learner will learn a wrong concept based on this hypothesis. In fact, we can generate out the additional hypothesis between the G4 and S4 boundary as well. We will see how to do that later. But I hope this much gave you some idea about what we really intending to do. So any
Ma'am,
questions so far, students? Yeah, please tell me.
Ma'am, so if any new data comes, new record comes, that should be
Uh,
consistent with all the three.
it should be consistent. If it is not consistent, what should happen? Your learn. That's what I told you. Learning is a continuous process. So which simply means if it's not consistent, it should improvise. Your specific boundary should improvise, and your uh, general boundary also should improvise. It should be a continuous process. And if you're testing on some example, if it's not a training example, if it's a test example, if you're testing your hypothesis on a test example, and if your hypothesis is not inconsistent, that means your learner has not learned it properly, or the training examples were not sufficient. You can conclude certain things like that. If it's a training example which is not consistent with the existing hypothesis, your hypothesis should improvise. If it's a test example and if your hypothesis is not consistent with that, then that means your learner has not successfully learned that concept, right? So any other questions, students, before I'll take another 10 minutes. I want to wind up the class now, but we did not start the program. Now, one thing about your program is I found a program. Definitely, I did not sit and code that. I only fine tune some portions of the existing code. Okay. So one thing about the code that I am going to give you for candidate elimination is that's a best possible program for candidate elimination, right? Meaning the number of lines of code is less and you can easily learn it for your exam, right? So you can actually exactly the way what we did, right? For the exact way as we did for our the steps what we followed, right? So the steps what we followed for our problem solving, if you try to do that, then the number of lines of code will be too much, and we've not done that. We've just tried to make it little simple. We just try to cut short the number of steps. We try to take some shortcuts there, but the goal is the same. The goal is the same, and it's going to work very similar to what we are expecting, but we have taken certain shortcuts in the code. So I repeat, we're not followed the exact same procedure as we solved the problem in the program. We've taken some shortcuts, but the ultimate goal is the same. Just a second. Another 10 minutes, please bear with me. Because I know otherwise I really cannot meet you till Thursday and it's going to be very bad. Okay. So, okay. Just a second. Okay, so I've just worked on some training example here, right? Anyway, we could actually change it. We'll go to the same training example. I think it's weather.csv. Yeah. Okay, so the shared screen is visible to you. So let's take this only as a training example dataset. Let's not go to this tumor.csv as of now. Let's work on weather.csv only. Okay. So the same thing, the same training example, the 4 training example, the same target, the same attributes here. Let's go through the code here. For this code, we're going to use 2 libraries. The 2 libraries are NumPy and Pandas. Since we know that in Python, we don't have a specific, array data structure. If you are performing any array operations, and we generally use the NumPy. And for any data frame and all these data, reading into our program, we use the pandas library. So we imported these 2 libraries, NumPy and pandas. So initially we are working on this weather.csv, right? So it is weather.csv. So from the panda library, we have a function, we have a method here called as read CSV, and we are passing as parameter the file which we have to read. Okay. And I'm just printing the data, whatever has been read. So data is simply going to print that data, right?
It's taking the first row as the
Yeah. So it actually requires, okay, not required for weather.csv. I think training examples.csv has a better option. Yeah, I had changed that here. So the training example, yeah, it's taking the first row as the attribute. So I'll take this training underscore examples.csv. training underscore examples dot CSV. I'm just printing the data, whatever I've read. So now it's better. So I have two targets, yes and no, over here. Now what I'm doing here is, please observe here students, I'm just trying to separate the concepts from the target. The target is this, enjoy sport is the only target. So I want to separate out all these columns from sky till forecast from the enjoy sports. I'm just putting that in a separate array called as concept. I'm going to put the separate array as target. So concept is a numpy array, np dot array of the same data. Data is whatever CSV that we have just read. So the two parameters are rows and columns, right? So rows and columns. It is just colon here because I'm reading all the rows. The first parameter here is simply telling I want all the rows. I want all the columns except the last column. That's why -1. So -1 definitely indicates the last column. So that's why all the columns minus the last column, right? So when I do that, I'm just printing concept. So concept is an array with all the attributes except the target attribute. I've just separated the concept from target. So any clarification so far, please ask me. Now the target, so target again, I'm going to extract out the last column or the enjoy sport, right? So it's a numpy array. I'm extracting out from the data frame all the rows and only the last column. That's why only -1 here. So once again, when I run that, yeah, when I run the target, so I have the target array over here. Now here is our main function. So this is a shorter version of our candidate elimination. I told you, if we look at, there are so many other variations of this program that I saw, but then they're really lengthy, right? So even though they are exactly the way we solve the problem, they're very lengthy, and it could be difficult for you to learn for your exams. This kind of suiting what is required for our candidate elimination. So we'll go ahead with this function. Okay, this is sufficient. So learn is the method. Learn takes two parameters. That is the concept that we have just, the concept array that we have just created, and target array that we have just created. Okay, the two arrays, the two data frames. Okay. Now what I'm doing here is, so initially in our problem, so please keep your problem, in case you've solved it, please keep it with you. So the very first step is your specific hypothesis is all null and your general hypothesis is all question mark. Right now what I'll do here is, instead of initializing it to all null, I'm just trying to be a little better, right? So I say I'm using these I comma h in enumerative concepts. So its enumeration will generally start from 0. So on this data frame concept, I'm enumerating from 0, 1, 2, 3 as the index values, and h is the first row, the second row, the third row, and so on and so forth. If target of 0 in the first iteration, if target of 0 is equals to yes, right? So your initial specific value, I did not initialize it to null. Whatever is the first positive value in my training example, your specific hypothesis is going to be the same thing initially. Right. So based on this, your specific hypothesis initially will be the first training example that is positive, that is sunny, warm, normal, strong, and same. Right. So why did I do that? Just to cut short and make it simple for me. Right. So concepts of I dot copy. So we've put it in a specific hypothesis. So you can definitely hear the bell ringing, but I will take the liberty of extending it for another 5 to 10 minutes maximum. Okay. I'm just printing the specific hypothesis. So in fact, if I run this, you can check that your initialization of your specific hypothesis, this is what we've printed. So the very first training example, whatever the concept was, that is the same thing of your specific hypothesis. Now, general hypothesis, we gave out 6 question marks. We gave out 6 question mark because there were 6 attributes, right? A is a target attribute. But now we're going to do 6 cross 6. We're going to do 36 question marks. Why? I'll tell you again, to make it much simple for us, right? So we are giving question mark 6 cross 6. So we're giving question mark for the range of length of specific hypothesis. Length of specific hypothesis definitely is 6. Range is going to give us a value from 0 to 5. So I gave 6 question marks. I want that again in an inner for loop. So I want that to run again. So that is 6 cross 6 question mark. So that's what we have here. We have 6 cross 6 question mark. And why did you do this? We did not do this in the problem. Again, to make it simple for us, in our problem, we only gave this as our general hypothesis initially. But here we're giving 6 cross 6 hypothesis, 6x6 question marks as our general hypothesis. So this are initial general hypothesis, and we have printed. We have printed the initial specific hypothesis and the initial general hypothesis. Again, we are looping on the concepts from the zeroth iteration, from the zero to the first concept and so on and so forth. If target of I equal to yes, right? So we're working on a different data set. So if target of I, if it is a positive training example, please observe here students. For x in range of length of specific hypothesis, that is x is going to range from 0, 1, 2, 3, 4 and 5. If h of x, if hypothesis of x, if h of x, so h is this, the concept, if h of x is not equal to specific, so h of 0 not equal to specific of 0. So initially your specific of 0 is this, right? Specific of hypothesis is this, and your first training example is also the same thing. So you don't find this mismatch at all. If there was a mismatch, then you had to do something. There is no mismatch at all in the first iteration. It was a positive training example, but there was no mismatch because the first training example and the initial specific hypothesis, they are equal. Right, the same thing would go ahead, and the second training example, when we go to the second training example, it is still a positive training example. So we check if h of x, if h of 0 is equals to specific hypothesis of 0. Your specific of 0 is actually initially this. So there's no mismatch, there's no mismatch, there is a mismatch here. So if there is a mismatch, if h of 2 is not equal to specific hypothesis of 2, I'm making specific hypothesis of x equal to question mark. I'm also telling general hypothesis of 2, 2 equal to question mark. General hypothesis of 2, 2. 2 second row, second column is this, and it is still question mark. So there's no action, but we're just making sure that it is a question mark, right? And then we go ahead, we go to the third training example. When we go to the third training example, this if condition is not true because it's not a positive training example, but the target of I is equals to no. In that case, what I'm doing, again, I'm running a for loop from 0 till 0 is not equal to specific of 0. Right? So if h of 0 is not equal to specific of 0, it is true. Right? So far it is true because if your specific of 0 is sunny and it is rainy over here. So if it's not equal to, then we're just making sure that we are putting a question. If, sorry, it's over. Yeah, it's over here, right? It's over here. If it's not equal to specific hypothesis, we're not doing anything about the specific hypothesis, but in the general, so general of 0, 0 equal to specific of hypothesis. So general of 0, 0 was question mark. We changed it to sunny. We changed it to sunny, right? Because specific of 0 was sunny. Else, if it's not equal, then only we got to take this question mark. Otherwise, it's a question mark. So the second thing is cold, and there is warm there. So it's not equal. So in that case, again, we change it. So general of 1, 1. So general of 1, 1 equal to warm. General of 1, 1 was question mark, but we changed it to warm. The general of 1, 1 was, okay, there is some problem here, right? So my code is actually not running properly. It's not showing the right output here. Yeah, because I have to do some changes here till now, students. Okay. So the problem here is, yeah, I'll tell you. The next time we're going to check if it is a negative training example. Similarly, we're going to check for all the attributes. Wherever there is a mismatch of the attribute, we're going to the general hypothesis and we're changing general hypothesis of 1, 1 or general hypothesis of 2, 2 or 3, 3, wherever, and we're changing the value to exactly this value of the specific hypothesis. But if they're equal, if your hypothesis, existing hypothesis and a negative training example, they are equal, then we go to the general hypothesis and we place a question mark. So we're going to go on printing all the steps of the elimination. So we're putting this inside this for loop. The whole idea is we see a lot of question marks. We see a lot of question marks in the general hypothesis. So we say that wherever you find question mark, I got to place 6 question mark here because there are 6 attributes in this training example. So that was a mistake. So when I place the 6 question marks here, so I'm just telling that wherever you find 6 hypotheses, the index values of that, right? So wherever you find the 6 hypothesis, go to those places and remove those 6 hypotheses and give me only the maximally specific and maximally general hypothesis. So this is the call to the method learn with these two parameters. It's going to return as two values, that is S final and G final. So we're finally printing the final hypothesis, which is, yeah, now it's working fine. You can observe that here. Your final specific hypothesis was this in our problem. So if you can see that, yeah, that's what we got. Sunny, warm, question mark, strong, question mark, question mark. So sunny, warm, question mark, strong, question. And final general hypothesis was these two. So that is, we have two options in the general hypothesis. Yeah, the two options in general hypothesis: sunny with all question mark and warm with all question marks. Sunny with all question marks and warm with all question marks. You can see that. So initially it's going to be all these question marks. Then we changed, sunny of, general of 00 to sunny, and general of 11 to warm, right? And a general of probably 5 to same, and then we saw that, and then next time when they were equal we changed it back to question mark next time. Then finally we removed out wherever we saw only question marks. These were, we ran a for loop to remove out all of these additional question marks, and we only retained the final specific and the final general hypothesis, right? So this, according to me, among all the versions of the program that I saw, this kind of the best version. So I think this is better for us to use this code. Okay.